So yeah, welcome to my talk about automation and Isabelle's analysis. It will be, I mean, yeah, I don't know if you, Shankar, if you want to talk directly afterwards or if you talk in 1 hour, like what's now's the time to do?
No, right afterwards.
Okay.
Back to back.
So yeah, I will talk more about, I would say basic proof methods, but which are very helpful in Isabelle. Unlike big methods like SNT or SETSA, but which are possible to use in a higher order setting or in a non-finite setting, especially. Okay. Yeah. What is Isabelle's analysis? I will talk more about this tomorrow, but we have the basic analysis stuff for most mathematicians, I would say. We have real and complex numbers, we have topological and metric spaces, we can talk about limits, continuity, we have Euclidean spaces, we have derivatives, integration, measure theory, probability theory, all this stuff. Now, what are the problems we are having on a regular basis? So we want to reason about non-linear equations. We want to reason about big operators. So we have essentially some higher order operators operating on functions. We have transcendental functions. We have parameters. So even if you have a linear equation, in a lot of cases, of course, we want to parameterize it, and it's not applicable, or we cannot just easily call some linear arithmetic on it. And of course, it should be extensible, so it should be easy for a user to come and add new rules, add maybe a new automation, specialized automation. So what I want to focus in this talk now is how we handle morphisms and a little bit more. So how do we handle, for example, continuity? Especially how do we prove, or including how do we prove that a set is open or that a set is closed? How do we handle measurability? And so the function is measurable, so the set is measurable. How do we handle limits? How do we prove in a nice way for a composition of known functions that a certain, let's say, reach a limit and what this limit is? Or how do we prove certain goals of this shape? And also about differentiability, of course. And as I said, we want to be very generic, so we're not only talking about Euclidean spaces, but we talk also about more generic, like topological spaces or maybe metric spaces in this direction. And the usual tools are a combination of rewriting and classical reasoning. And so first I want to give a short overview what are the traditional proof methods in Isabelle and how we can extend them to solve this kind of problems. So the generic traditional methods, let's say, is a simplifier which has conditional rewriting and plugins. We have classical reasoning where we have entry and elimination rules. I'm not sure if most people are familiar with these terms. I will show a simple example. And then, of course, we combine these two methods by simplifying, applying logical rules, simplifying, applying logical rules. And then there's a tableau prover, and I think it's a very big name now. Sledgehammer is something everybody's somehow familiar. Sometimes it works, but unfortunately for me, at least if you have very abstract proofs with a lot of higher order functions or talking about sets, Sledgehammer often fails for me, unfortunately.
Which tableau prover do you mean?
It's a blast.
Ah, blast.
So,
Sledgehammer is shipping stuff out, what, to a SAS or something?
to a first order theorem proofer, automated first order theorem proofer. Usually it's like SMT set 3, or we have some first order like Vampire or Schwarz. Yeah, so the simplifier, it's actually, so the first versions of the simplifier was added in 1989, so it's quite old now. But still very powerful, and by adding simple rules, you can keep up with your problems very nicely. Or the simplifier keeps up with your problems, I would say. So it has conditional rewrite rules where I say, okay, and this is assumptions, we can rewrite this, and the simplifier, of course, tries to simplify this to true. We have but of course sometimes we need to add congruence rules, which are especially important when we have something like big operators where we want to prove, where we need the fact that we actually have a parameters from a certain set I, and then the simplifier can rewrite f to g under the assumption that I is actually from this set. And this helps especially when you have conditional rewrite rules and measures that you sum up between 0 and n, and you need the fact that actually the parameter I is non-negative or something like this. Another addition to the simplifier, which turns out to be quite powerful, is the splitter. So the simplifier walks over the term, and when it discovers that there is actually a case statement like if, it can actually split it up. And of course, Hall is a classical logic. We have always decidability, so we can add, can split on arbitrary conditions. Then the simplifier allows to add plugins. So if the simplifier walks over your term and tries to rewrite it, and the user can now add a plugin by saying, okay, if this pattern is reached, calls this ML function, and the ML function then tries to normalize or tries to rewrite this function into a normal form or hopefully to true or something like this. And also equally important, I would say, is there's a global rule database which can be either set up by where packages can add rules. For example, the data package in Isabelle adds a lot of rewrite rules as a simplifier, but also, of course, if you develop your own theories, you can always add rewrite rules as a simplifier.
How evil can be the plugins, right?
I mean, the plugins need to produce a proof. So as if style.
So it's all checked again.
Yeah, it's all checked. Yeah. I mean, of course, you can always implement the Oracle in Isabelle and say, okay, just admit this, but then it's specially marked as being. And I should also say that there's no check for the rules, of course, of normal forms or something. It's if you write the looping, if you add a looping set of rules, you're zero for them usually. There's one exception. It discovers permutation rules. So associativity, for example, which allows us to add permutation rules, to add commutativity rules, and then rewrite modulo AC, or it's a simple form of rewriting modulo AC. Then the classical reasoner was added in 1995. It's mostly used in the form of auto. But first, what we call introduction elimination rules. A introduction rule is a rule of this form where we actually match our current goal on the conclusion of the rule we want to apply and replace it with these two goals. And then the elimination rule now tries to match one of the assumptions on the first or on the couple of first premises of our goal. So a proof method. So as I said, again, we have a rule database for this kind of introduction to elimination rules, and with two different parameters. One is a safe rule, and the other one are unsafe rules. Where safe rules guarantees that you do not lose information when you prove. So you can always split a conjunction, but it's if you add disjunction on the left or disjunction to the right, this is not a safe rule because you lose information and you may go into a proof set which is not provable. Yeah.
I'm just thinking of whether the safe here is really the same as an invertible in proof theory.
I mean, it's just a flag you set as a user, and then it's your decision if you think it's.
So is the intention of the meaning of the flag whether the rules are invertible or whether errors that somehow be introduced?
Yes, the intention is that the user tells the automation, hey, just always apply this rule when possible. It's allowed. You don't make any. It always makes sense, or you don't lose any proof path. And unsafe means now you need to be careful and only in the part where you can backtrack actually. Then auto. Auto now is a combination of this kind of proof search where we just apply logical rules and then try to break down our proof into simpler goals, of course, and we loop it together with a simplifier. So the idea is to apply safe rules and cause a simplifier until it terminates and cannot further normalize it, apply logical rules of this form, and hope to break it down into form so that the simplifier can do some work again. And also there's a mode where it tries to solve one goal in one step by doing only logical rules where it can also apply unsafe rules. Also does a little bit of instantiation, but that's very mysterious to me actually how much instantiation it applies. Sometimes it works very nice, sometimes it doesn't work. And then BLAST is a tableau proofer which uses also the safe and unsafe rules but does not do simplification. And then there's, this are the general methods everybody who's using Isabelle is, after a couple of days, maybe weeks, very familiar with. But there are, of course, when you do analysis, you want to have more powerful algebraic rules, algebraic methods, or arithmetic methods. So we have a couple of explicit, I call them explicit because they're not integrated with auto. It's you need to explicitly say, okay, now apply algebra or apply approximation. And also the statement needs to be in the right form. So algebra is applying Grübner basis. We have this approximation method which applies interval arithmetic on formulas with transcendental functions or on strict inequalities on transcendental functions where you can have variables, but the variables need to be bound, so we can actually do interval arithmetic. And there's something called sums of squares, which we reported from Hölzl, which tries to rewrite a polynomial in X into a sum of square polynomials, so we can easily prove that it's not negative, for example. And then, as I said, we have this simprox where we can integrate plugins into the simplifier, which is, for example, the linear arithmetic is integrated like this, and also was, in my opinion, maybe more important even as linear arithmetics, that they have a cancellation which tries to, if you know that this is an additive group, and then we can eliminate, for example, the one easily, or additive group. Then we can eliminate this one here. It would be hard to find a set of intro elimination group which would do this step. By special methods, it's very easy. Okay. And as I said, I would also add to automations, usually adding a set of implicit rules, which sometimes just having a set of rewrite rules feels also very good, like automation, etc. Okay, now to the specialty for analysis. So how do we prove measurability, continuity, and then, for example, how do we prove that a certain function has a certain limit as a point? Well, the idea is we use just introduction rules. It's similar, very similar to how type class resolution, for example, works usually in POC, I guess, or how it works in Lean. At least that's what I know. There's a parenthesis missing. So the idea is we want to prove a statement like this is continuous, and then we break it down along the syntactic structure of the function. Here we have a constant function, so we have a rule for constant functions. We have a rule for multiplication, so we can break it up here. We have a rule for addition, and at this point we have a rule for logarithm, which breaks up into these two parts, and then we will end up with where the user needs now to show how that f is continuous and that f is not negative, is positive, and usually that's in our assumption, so that's in our context. So the automation will be also able to solve this. But the question is, of course, is there a fixed rule format users should follow to when they add a new rule, when they add a new function and prove that it's continuous or measurable? How does this rule need to look like? How do we handle higher order functions? Like we want to prove that the least fixed point of something is measurable. That's the question I want to answer in the next slides. So first, what are the structures we want to work with? As I say, we want to reason about continuity and measurability, where we have spaces, but there's a problem in Isabelle. So topologies are quite nice. We add to each, it's a type class, so each type has a space associated to it, or when we when we have a statement that something is continuous, we know that there's a topology. But if we want to talk about measurable spaces, and Isabelle says our explicit data we need to carry around, and also the measurable spaces have an explicit set assigned to it. So we need, in some cases, we need to do a second proof that actually a value, for example, if you have a constant function, that the constant value is actually part of our space. So that's a separate proof. That's one of the limitations of HOL. When we would have data dependent types, measurable spaces would be much easier to handle. Then of course we have morphisms like continuous and measurable functions. We know that they're closed under composition, and also of course important when we want to talk about morphisms with multiple parameters, we need product spaces. But what we usually do not have are function spaces. We had it in the best talk today. Topologies are usually not closed under function spaces. Also measurable spaces are not closed under functions. So we need to, especially when we want to handle higher order functions, we need to have a special form in our rules. So one obvious idea would be to add just a composition rule now to our set of introduction rules we want to apply. But there are a couple of problems. One is, at least in Isabelle, the higher order unification would always match when we have an application, would always match because it could always assign to f or to g actually the lambda x dot x term. So it would start looping, it would always match the composition rule, which is of course not what we want because it doesn't terminate anymore. But even if we have a test to say that f and g are not allowed to be just the identity function, we have still the problem that we may not know how to split up our there may be compositions of functions which are only in composition, are actually continuous or measurable, but not each single constant may not have a nice measurability or continuity rule. So when we do the split up, we would need a quadratic number of possible splits. And then we need as I said, we need special handling for binary functions for big operators. And interestingly, as far as I understand, this is what is done in proof power. When they want to prove that something is continuous, they have a method to rewrite functions or terms like this into a composition like that, where we say, okay, now we have a binary operator, so we need to have a pair constructions of these parallel functions, and then we can split this up, and then we can have a introduction rule for continuity matching directly on this composition operator. But still, then we have a problem how to handle big operators. How does it know that some functions are only need to be composed to be actually continuous or measurable? And what do we do with side conditions like for Ln? We need to have a proof that the result or that the parameter to Ln is actually non-negative, is actually positive. So our idea is, or the maybe more like obvious idea, but it's not always implemented like this, is that we have this general rule format where question mark means that this is a meta variable. So when we apply the rule, these are the functions which will be instantiated. So we have a constant c, a couple of parameters to c, and a couple of let's assume we want to prove that c is continuous. So a couple of parameters where it should be continuous in it. So we have actually functions depending on our input value. So we don't know we know what our range is, but we don't know what the domain will be of f and g, and this needs to be computed by further applying further rules. And of course, the idea is that here we just have a list. Yeah.
Do you know how to do it in proof power? Is this automatic?
As far as I know, I never use proof power, but there's a paper in the Journal of Formal Reasoning, and I think they do it automatically. They do rewrite this automatically into this form, and then they apply a fixed set of
Yes, we did something similar when we were doing integration.
Mm-hmm.
So in Haskell there's a tool that actually gives you the point-free presentation.
Mm-hmm.
So you rewrite it in the point-free presentation, and
Yeah.
you can use these tools.
Mm-hmm. Yeah, but I think it's a little bit. It's first hard to work with, in my opinion, and it's not as flexible when you have this format here, because for example, what do you do? How do you now add the information that f is, for example, positive? That the result of f is positive.
Yeah.
And here you just add it here as an additional goal you need to prove for all x in mass space f.
No, we just thought it was very cool that we got everything
Okay, yeah.
glued together, but it's
Yeah, I mean it would be nice if it works, but I think this are at least that's the general rule format I try to follow. And it's important that even when we only have one parameter, that we add a additional function parameter to say, okay, now we like the continuation. If you walk over your term, that we always have a placeholder where you can have a composition of your terms. Yeah, let's take a look at some examples. So 0 for continuous, for constant continuous function, and here, for example, I mean, as I said, and for topologies it's not a problem, but for measurable spaces we need to prove that C is actually in the space of B. Identity function, when we have one fixed constant exponential function, for example, like here, then of course we still add, we don't just say f exponential function is element of the continuous functions from A to R, but we actually say, okay, now we have for all functions f from A to R, we know that the exponential function composed with f is going from A to R. So it's also universally quantified in A and f. So now, like when we have the logarithm, we can add additional parameters on our input space. Like here we can say, okay, now f needs to be positive. Of course, one alternative way would be to have subtypes and to encode it in the range of the domain of logarithms, that we only talk about positive real numbers, but usually that's not a very nice compositional way, and it's very hard to operate with this kind of structures. And this allows us to be in a very general setting without a lot of problems, I would say. If you have multiple parameters, it's also not a problem. If you have multiple parameters into different spaces, like here we have scalar multiplication and vectors, we just say f is now into R, and g is into R to the n, so it's the vector space. Big operators are actually also quite easy, assuming that the index that we sum over is not dependent on our input value of the function. If it is dependent, it gets of course very complicated, and then it depends. There are some topological functions for which this works, there are measure spaces, but not others. Of course, we need to prove that I is finite. This depends. Sometimes this is defined to be 0 when it's not finite, so we can even drop this assumption. And we just need to prove that for each element in our index set, f of I is continuous or is measurable. So that's quite nice. But there are of course more complicated higher order functions like the integral, which takes now. So this rule says that the integral parameterized over a measure which is parameterized by x, integrating a function which is also parameterized by x, and integrates it over y, is measurable if f is measurable on the product space of A and B, assuming that x is A and B is the measure space from the measure M, and M is a probability space is a measurable function from A into the probability spaces of B. And here it's also important part that now we have at some point we have this goal, and we need to also have something to reduce the pair construction or the match we have here internally, and we need to work with this match and resolve it somehow. So the easiest part is usually to rewrite this just into lambda p and then f applied to p.1 and f and p.2. This works really quite good. Then of course, how do we do is deal with even more complicated higher order operations or some more special ones. Depends on what you want to see. Let's assume we have the extended real numbers, which form a very nice complete lattice, and now we want to prove that a function can be constructed, or a function constructed as a least fixed point is actually measurable. For this, we need to prove that it's continuous f, and so the function itself is continuous, and that's a function that is invariant under measurability. So when we put in a measurable function, that's a transformed function on our function that is again measurable. Now when we apply this, let's make a small example. So for example, we have streams of extended real numbers, and we just sum them up. So we take the head element of omega and apply f to the tail element of omega, and then we end up with two rules. First, we need to prove continuity, but that's again, continuity is as we have seen before. We can just apply our introduction rules. And here we have now the problems that f is not in our standard rule format. So this f here is now can be seen as a constant, and we need actually a method to extend this from f element stream R to R to actually, for all functions g into streams, f can be made, f under g can be measured. And we see that's a problem when we want to apply it, the measurability here, because f is not applied to tail in this case, so we need to have some method to extend it. And then that's a special method that I implemented, for example, in Isabelle, which does exactly this. So when it proves measurability, it collects all information from the context and transforms a rule like this in the context into, okay, now for all g, and then measurable spaces c, this is extended. And also for like product spaces, this needs to be extended like this. Okay, and then there are a couple of specialities, like how do you handle countable discrete ranges if you talk about measurable functions. There's a special rule like this, where you say, okay, now we have a function g going into natural numbers, and we can just, when we want to prove, when g of x appears in our term, we can just replace it by a new constant we introduce. But of course, this is not something we find we cannot just apply unification and then use this here, but we need to actually have a method which goes through our term and finds the points where we actually have discrete and countable spaces. Then another nice thing is that we often want to prove that open sets represented as set comprehensions or measurable sets or closed sets are actually, we want to prove that sets represented as set comprehensions are open, closed, or measurable. And for this, of course, we need a lot of predicate rules, saying or relation rules, where we say, okay, now when I have less, then I can prove that f of x less g of x, the set of all this x is open. We need to reduce it. We can reduce it to just saying that f and g are continuous. And then, of course, it's important to have all rules over the logical connectives, and then, of course, quantifiers. So you get a very nice, results also for open and closed. Okay. Then I said also we can extend this. How do we work with limits or derivatives? So one problem is, of course, when we look at this rule, and let's assume the problem would be if x plus y, usually we would expect, okay, the limit of x, f of x plus g of x is the limit of x plus the limit of g. But then, of course, this is a very fixed shape of our term, which we want to avoid. So what we do is just add an additional equality. Similar here for logarithms, of course, we want to have also an additional equality. And as a user, usually if you add a new rule, like a limit rule, you usually forget to add this equality. So now we have a special method when a user adds to our database of limit rules a rule of this form, it adds an additional, a rule of the form where we have here a constant and not a variable, we add this additional equality. And then the nice thing is, if usually we have some on both sides some terms which are equivalent modulo AC writing, distributivity, and then where we need to just bring division on the right side. So there's a special set of simple rules which do all this rewriting for us. And then usually it's just applying all these introductory rules and to simplify using fleet sums. And the nice thing is derivatives are now very similar, so there's no big difference actually. Yeah. So to come to the conclusion, first, measurability works quite good, which is very important because measurability proofs appear a lot in measure theory. For continuity, differentiability, and limits, it also works quite good, but not as good. The problem is that for measurability, I implemented a own proof method because it appeared so often. At some point, we should implement similar things for continuity and so on. Yeah, as I said, otherwise mostly you apply introduction rules and then call the simplify to resolve the rest. And also, it's interesting that it's also your method gets much more powerful if you add special cases like discrete space that you say actually, okay, the natural numbers and the Booleans are a topology, and then you can define a lot of nice rules, even if you usually do not care about if a function from net to net is continuous, because it's obvious, but it's very nice. Yeah, okay, that's all. Thanks for listening. Are there any questions?
What are you using this? What are you proving? Is this toolset?
So for example, measurability, of course, is very important for probability theory, and we have it's essentially, for example, we have a proof of the central limit theorem. Here, this essentially to again and again have shown measurability of functions you want to integrate over, and of course, usually it's just a small combination or composition of 3 or 4 or 5 constants, but if you do not have automation in this regard, you always need to write 10 or maybe even more lines to prove measurability. And if it's just if it's just by auto, it makes it much more easier.
So you can do your high school calculus class
Yeah.
in Isabelle.
You can, yeah. Also, your undergraduate, the first couple of semesters should be fine now. I mean, I will talk about this more tomorrow, what we actually have in analysis. Any other questions?
So did you think about a more algebraic approach to measure theory?
To measure theory?
Yeah.
And in which sense, more algebraic?
So by quotienting, I mean, the formulation in set theory is very, it's a bit convoluted, although it's kind of, I mean, people like Tao have been, have been emphasizing that things should be more stable, more categorical approach.
Similar, you go from topologies to locates, and then you go from measure spaces to. No, I never thought about this. I mean, usually.
Because then things become more algebraic,
yeah,
and therefore easier to formalize.
I mean, I would say in analysis you want to reason usually about your function spaces, and especially in HO-edit, it's usually very difficult to construct this new kind of type, or this. For example, the problem is that, as I said, measurable spaces I usually have a set, a subword set, an explicit subword set, and this cannot be transferred into a type because the set can be constructed inside of a proof, and you cannot construct a new type inside of a proof, for example.
So you should go to Lean.
Yeah, I mean, I'm working on this, so. But it's a good idea. Something I should look at. Yeah.
Which tactics can one invoke to get these?
I mean, usually it's either the user directly invokes auto and gives it
These are built into auto.
Yeah, auto is built into you write your statement, have or show a certain statement, and then you give a tactic to solve this story.
Is there any way of getting the steps that you've mentioned, seeing what's happened?
I mean, you can always generate proof objects, which are huge and usually don't work as well in this actually.
So
but you can also, for example, for the simplifier, you can you can activate tracing of the simplifier, and it gives you a list of.
watch the trace.
Yeah. But it doesn't. The problem is that it does not work for class categories now. So you don't see which kind of introduction rules are applied. You only see where at which positions are simple rules are applied, reward rules are applied.
So you may well end up not really understanding why
Yeah.
you've been.
Well, this is I have made the experience that this also can happen when you use when you write down more explicit proofs.
Oh, certainly.
Sometimes if it's abstract enough, that you don't know what's going on.
I wouldn't disagree.
So if I'm totally new user, how often will like this automation loop, for example?
Oh, that's a good question. I mean, if you follow your rules, it usually does not, because you really follow the syntactic structure of the terms. But then especially if you have, here I had some problems where my method introduced certain things in the wrong order, and then it didn't work as nice anymore. Or when you do not. Here, for example, you need to be careful that you. At some point, I thought it would be nicer to always unfold it at this point, to always apply a case constructor here. But it's just nicer to go the other way and say, okay, when we have a match statement under the lambda, immediately replace it by f.p1 and f.p2. And have something like the splitter doing this, because the case can be actually happen inside of the term and not directly.
So this is when you are sort of designing the rules.
Yeah.
But then the user of your formalization is safe because you have designed it correctly.
The user also often needs to add new rules. You
Okay.
construct new functions and need to add that this function now. I mean, especially if you have recursive function, you need a lot of side conditions as well. When the user does something wrong, adding the wrong rule, of course, it doesn't terminate. But usually, it's safe.
And is the time taken for a tactic to sort of come back?
This is super
Milliseconds
fast.
or-
Yeah, this is super fast. I mean, the problem is, of course, when at some point you need, for example, to prove that your term isn't your constant value is in the space. Then I call the simplifier, and of course, sometimes the simplifier calls linear arithmetic, and then this may take some time. This can take a long time, but just applying these rules, of course, is a matter of milliseconds. It's like I don't know if Acta has type classes, but in Coq if you have a straightforward type class search, it's not a problem. But if you get into more complicated tools in your type class, as well as understand.
Andreas will be able to tell you that. Instant search in Agda.
Okay.
Just more general question. Does it ever happen that I don't know, you've got your ISAR document and you prove something with auto, but then in the next version, auto's changed because you've added some more rules?
Yeah.
Does it ever break?
Yes, a lot.
It does.
There's usually a huge list, and for each new release, and Isabelle, you have a huge list. First of just names changing, but also sometimes changes in the SimSet. And the worst case is, of course, when somebody decides to switch a rewrite rule from one direction, which doesn't happen too often, but it can happen. Or is that somebody decides to add a new rewrite rule to the SimSet, and the user has somewhere adds the reverse of the rewrite rules, and of course you do. This happens, yeah. The nice thing is, if you have your development in the AFP, you take care of updating it to the new Isabelle versions. So,
Is that done by hand?
Yeah.
Wow.
I mean, usually if you change something, you exactly know what to change when it breaks. So it's quite okay, I would say.
So to me, this slide looks really more like type system than what I would call automation.
Yes, it's true. I mean, it is in some sense a type system. You need to at some. Maybe a type system is a very special form how to. Especially, for me, it would be strange to have a type system which is not closed in the function spaces.
Yeah. I guess you are saying that you need to put it in as an automation because the Isabelle type system
Yeah.
is
It's too restricted. I mean, you could, in dependent types, you could of course introduce your function space of measurable functions, but then it's super annoying to, because then you have this, you again, and you essentially it's this part, right? You know that addition is continuous or measurable when you get a pair into it, because otherwise you cannot express it. So you need to do this phase here when you talk directly about measurable functions as a single type, as a bundle type. And yeah, I would say usually do not want to do it, especially not on an analysis where you usually work on the more elementary side of continuity and measurability. And yeah, that's my experience at least.
Wonderful, yeah. Thanks. Okay, we can take a short break if you want. And, so, by the way, this is kind of an open session, so we can. Whose flash drive is this?
I don't know, it was there before. Your stuff was also in it, but I guess yours, is it your flash drive?
It's